was having trouble connecting to internet. But now it seems like I'm in. All right, as I'm loading things up, how is module 3 going? Do we have questions so far? What are we working on? Which part are we working on today? For the main thing coming up is like module 3. Yeah. Okay. Let me close out these other tabs. All right, what are we trying to do with a spring mass damper? Just run through, make sure all my stuff is there. There's our spring mass. Oh. Delete all that. So trying to like use 3 different methods for spring mass or something else. Yeah.
I've just barely started it.
Just starting. Okay. Yeah.
I have a question on the last part of that, where it's asking how many time steps.
Yep.
Is that just kind of a plug and chug? You test different number of time steps to watch it converge? Or is there an actual analytical way to say, hey, you solve for the number of time steps for it to converge?
Yeah.
Because I just played around with adjusting the time steps to get because you can get the second order one to converge faster than the first order one.
Exactly. Yep.
So it's just playing around with the time steps to get kind of an approximate.
Yeah. And here I'm trying to scroll back up to our like Hyun step integration. Just want to get rid of that. In here, there's like something different in this Hyun step. But anyway, like as when we talk about convergence, it's like it's on a log scale. So when we say like it is converged, if I'm saying convergence is 10 to the -7, I mean anything from here to there is like a factor of 3 to 5 different. So these are like, it does turn into, people talk about like numerical models as experiments, like my computational experiment, and this is part of the reason why, like you do have to try things, see what happens, and then analyze the results. Yeah, so I don't know if there is, because we do have like exact solutions, like we know what the answer to, like I know if I look at this spring mass damper kind of setup, if I know the initial conditions, I know exactly what it should be at any point in time. So I could have like an actual
Analytical solution.
yeah, at least like a number that I'm trying to get to. Like, but a lot of times you don't even have that. You're just looking at relative changes, like how much did the
Do the relative error.
yeah, exactly. Like how much when you predicted that it was 0.1 meters at 3 seconds, and then it changed by 0.001. Yeah.
So when you're trying to determine if it converged, I just plotted all three
Yeah.
basically, and then watched as they slowly got closer and closer and closer to the same line. That's essentially what we're doing.
Yeah.
Playing with the time steps until they pick the minimum number basically to the point where they all reach the same shape.
Yep. Yeah. Yeah, and that's a great like visual way of checking. Coming back up. When we were just looking at a spring and a mass integrating with that Hune step, I'm gonna change like, oh, too big. If like visually, if I use 21 time steps from 0 to 15 seconds, it just looks wrong. Not only is it jagged lines, like I don't have a lot of the precision that I probably want in this solution, but the answer between my like actual cosine of t and my blue line of that step, they're not the same. So there's always an error between the two, versus coming up here and saying, well, let's try like 51 steps. Now, at least in the that first oscillation, it looks a lot closer. There's probably a lot less error. And this is a great like visual check if you plot your answer versus what you expected the answer to be. It's a good way. I think it's a great way to look at convergence. Like, is it converging to one thing? And really, and even if you didn't have that exact answer, you could say for n in look at how, as I keep increasing n, the answer should get better as I increase like the number of steps. And in fact, it's all coming into one solution. Like it's all converging onto one thing. It's different than like steady state convergence. Like some people get that one a little mixed up. Like as t goes to infinity, this one's like for all time is the answer converged. Yeah. So yeah, it is a lot of numerical methods is a very sophisticated guess and check method. Which ends up being pretty good, especially when a computer is guessing and checking for you. And what was happening? Because I've seen this one before, but it wasn't doing that last time. Did anyone, when you were looking at like convergence of that hewn method, did anyone get a slope that was higher than 2 on a log plot? No? Sometimes, some people get like a slope of 4. And that's what I'm kind of getting here. Like from 0.001 to 0.01, it has a slope of 4 in my convergence. But I guess nobody else is dealing with that. It depends on where your last time step is, like where you're trying to converge. Yeah.
Was all that for 1.3 question 1? All that spring mass stuff? Because in our homework, it just like, it's talking about like using some same code from above, and it's talking about some function spring mass, but we don't have that.
Oh, that's in, like, if you click on this, like sometimes I use above because the questions used to be at the bottom of the readings, but it's, so spring mass is in this get oscillations reading. So do a quick search for spring mass, and then we've got this one. And then hewn step is also in here, so we don't have to, you don't have to like create your own hewn step. Like it's been done, and it's not even like the best integration method, but it's a nice introduction to like what's different between this one and Euler method. Those are kind of like, Euler is, if you're just getting started, it's a great like explicit method to see, can you integrate this? Hewn step is one level above that, where it's implicit integration. But there's plenty of great explicit like multi-step integration methods. The Runge-Kutta 2, 3, and 4, 5 methods are defaults in SciPy and MATLAB. But in general, you probably won't write your own integration functions unless you're, like, if you're optimizing code to put on a microcontroller, maybe you would want to like test a few different integration methods and then get like a bare bones integration stepper. So you can take like current, integrate it, and get charge on a capacitor or something on your like battery microcontroller.
Bracket method
Yeah.
for getting into the depth of sign F. So this is just getting into basically, I understand you're taking your function of x and you're finding the signs and how it changes incrementally. you're gonna notice it's gonna that you're solving for the zero.
Yeah.
So I get that. My question is just the syntax of this code here. We're taking sign out of the second index to the end of the array minus the first index to the last one.
Like second to last.
So basically, it's stepping through the array in this process, right?
Yeah.
So element 2 or index 1, element 2 minus index 0, element 1.
Yeah.
And it's going to go all the way until the end minus the one right before the end. Okay.
Yeah.
Yeah,
like one way you could do it is like loop, and always take I minus I-1.
This is just like a shorter version of doing that.
Yeah, because this is actually creating like two slices of vectors that are shifted by 1.
Yep.
And subtracting them all at one time.
So it creates one vector for one array in the end.
Yeah.
Basically, okay. And then the exclamation point equals is not equal to 0.
Yeah.
Okay.
Yeah.
Perfect. Thank you.
Yeah. Oh man. Oh, you should. Oh no. There's 3, but 2 of them. Three in front of they are different. You Yeah, it is. It was set up. So there's a range, which would be start step size, which would have been 0 to 1. It actually was 0 to 9. And that's why you get yours? Put a Oh, yeah, I was messing around with that one. Well, I think you're exactly right. Do you have but it's definitely not, like it's converging faster than squared, right? That one I see it once in a while, depending on where I'm evaluating what the error is. Because cosine, like if you're near 0 or too high or 4 high, then Taylor series expansion is 1x squared next to the 4. So you end up with like that second order convergence is already there. Like you're already converged to get 4th order. It looks like it converges much faster because you're near that. Sometimes I don't think I'm doing like the error where you have the error value. It might be well, like this is we're just looking at how does the method converge, we could use pen, we could use such spots, right? But anything, yeah. Because we're just trying to find can we create the cosine thing. I'm putting stuff in the wrong spot. So I just grabbed the 3 integration methods that we're trying to compare for our spring mass damper, Euler, Hudenstep, Runge-Kutta. I deleted the dock strings. Normally I don't like to do that, but I wanted to just show them all in one spot and kind of see similarities and differences. So like Euler step and this Hudenstep, it's the same thing. Like next state is state plus right hand side times some time step. The extra like correction is all within this for loop where we're saying don't give me that next step until you check it. Like go through some kind of iterative procedure and then keep updating the next state until it converges. Versus this Runge-Kutta, which is again, it's the same exact formula as Euler. The only difference is now we also create something called like a mid state, and there's higher order Runge-Kutta methods that use more mid states, but we're taking like right hand side times time step times 1/2, as if we're taking a half step into the next time, like where we want to converge to, or where we're like trying to look at, and then use that to recalculate like a new derivative there. So we have these 3 different methods. Let's see how they solve our spring mass damper solution. So what did derivs look like? What did you come up with? What was the first thing? What's the first output? We need, our state has 2 values, position and velocity. What is derivs? When I'm trying to output my differential equation, what's the first thing that I should get? If I give it position, velocity, what do I get back? Velocity and then acceleration. So this would be like state of 1, because state 1 is my velocity. And then what's my acceleration?
Going to be that function of zeta.
Yeah.
Anytime you see a velocity, anytime you see v for velocity, it's going to be state 1.
Yep.
Anytime you see x, it's going to be state 0.
Yeah.
So it's the same function above, just replacing V-nice.
And if we want, we can do 2 lines. So this is my SMD. Oh, too many parentheses. There we go. And again, I always check it. So if I'm at 0 position, moving 1 meter per second, then I have negative 0.4 like acceleration. So something's pushing me to the left because I'm trying to move to the right. It makes sense. If I increase my position, and let's say speed is 0, now I am being pulled back to 0. So it's always a restoring force, that's good. That means that it's at least in this case, it makes physical sense. Everything in our like spring mass diagram is something that's resisting speed and restoring the spring back to 0 of x equals 0. So at least intuitively, I think we're on the right track. So let's set up our states. State Euler. I guess first we should set up time. What's our omega 2? Let's do 6. We'll do, I want to have like 10 time steps per period, so like 31 steps. I want 2 states for every step in time. And I want to do that for Euler, Kuhn, and RK2. I'm going to do my fancy triple cursor. Start at 2 with 0 speed. And this first one I think is Euler, like that, if I could spell. This one is going to be Kuhn, RK2. Yep. I feel like this should have that underscore to match everything else, but too late. Already too deep. Oh, and we should put a bracket. RK2 step is not defined. I should probably run the code that I put in there, huh? Oh, that's not enough times. It's not enough. Oh, I should define DT too. If you don't define DT, then it's going to be whatever was in my namespace before. So I don't know what DT was, but it definitely wasn't the time step that I thought it was. At least in this case. T1 minus T0. Alright, is that good? Bad? The nice part is we have a perpetual motion machine. So that part's good. The bad part is that it's probably not right, since perpetual motion is like very much outlawed second law of thermodynamics. So if you're trying to say that your numerical model is predicting infinite motion, you're probably wrong. So let's increase time steps, right? Double it. Starting to look better. I'm trying to get Euler to converge, but we can already see that Hunstep and Runge-Kutta, they're done. Like, you don't need any more time steps here. Like, probably even with those 30 time steps, just like 10 time steps per time period, it was probably enough. We probably converge pretty well. Maybe not 10 to the negative 15, but probably like 10 to the negative 8 error, you know, at least like relative error. Definitely not like measurable. You can't get a caliper out and measure how big of a difference there was. So we can keep increasing. And in the beginning of the class, we started off with the discussion of like, how do you know what time step is the right time step? And it's not something that we can derive. Like, we can't write out an equation and say like, Euler method will always converge when dt is equal to square root pi something. Like, it just, actually, now I'm thinking about it, I don't know, maybe we could, since we do have an exact answer, maybe you could do a Taylor series expansion and like do a power series comparison between Euler integration and like cosine. I don't know if it would work, but I'd be interested to see if you could. So 121, still not big enough. But if, like, at this point, with 121 steps, there's no visual difference between Hune and Runge-Kutta. They're both the same answer. So those two have converged. So I could kind of say like, right down here, so I just added a title and said, once I hit 0.07 seconds for this solution, it's all converged. Like, there's no difference between Hune and Runge-Kutta versus in here, we probably have to get up to like Let's try 601. Yeah, even 601 is still, Euler is still not where Hune and Runge-Kutta are. 1201. Now, by the time we get down to 12, so another, up here we were at 0.07. Now we're at 0.007, like 10 times more, and we're finally getting to the point where it's getting close, but there's still some difference between the two. But just like, yeah, if I'm trying to like organize my results, and I don't like, there's too many floating point things here, so I'm gonna just 0.003. So now I've got like 0.079 and then 0.008 are my, at least what I found. And you can, those numbers, they can change. And again, we're on a log scale, like we're talking about convergence on a log scale. So 0.007 versus 0.005, no difference. It's the same time step. It's like the PAM can corporate tell the difference between these on a log scale. No, they're both the same. It's all the same. Oh, and the other thing, I always thought this was the better, but not everyone likes to think about like state space, or like phase diagrams, or phase, I guess like phase plot. Have you heard that term before? Not like phases of the state of material, not like solid liquid vapor, but a phase plot as in like, what is the state, like if you plot the different states. So here our state is position velocity, not temperature, pressure, density. Oh yeah, I should actually give it the same Euler. Hune, RK2. Have you seen this kind of plot, phase plot, before? Where you're showing like how are position and velocity related to each other? Do you know what it looks like if damping is 0? Yeah, what is it? For position velocity though.
It's gonna be oscillation.
Oscillation? All right, let's try it. Oh, what is it supposed to be? Zeta? I'm gonna hack my way in there. Oh wait, I gotta change these now. So Euler's still wrong. Like we know that Euler's wrong here. But Hune and Runge-Kutta did converge. What are they? What shape is that? So we get a converging spiral for, like, if damping is more than 0, then it should converge. Let's just hide our oiler because that one's just, it ain't right. What is that telling you? This is like, if you think about conservation of energy equation, x and v, so like 1/2 kx squared plus 1/2 mv squared is always a constant, and that equation gives you an ellipse that describes, like, and that ellipse is described by that equation of 1/2 kx squared plus 1/2 mv squared is something squared. It's like major and minor radii kind of squared. So in a phase plot, if you see a phase plot as like a continuous ellipse, there's no damping, no friction, nothing. It's just energy is always conserved, versus when we have, I forget what it started off as. Versus when it starts in one spot and then starts spiraling towards something, showing you that you're losing energy and it's all going to some equilibrium point. Anyway, thanks a lot. Thanks for joining. We'll be back Friday. Today's Wednesday. Yeah, we'll be back on Friday. Sounds good. Thanks a lot. Thanks a lot. Thanks, you too.